So in this section, we're going to start talking about calculus topics, and we're going to start with the concept of a limit because everything in calculus is based on the limit. This is very important for you to understand this, otherwise you'll struggle through the rest of the course. It's not hard. You really need to make sure that you understand this concept, and if you don't, please let me know and I'll help you with it. So a limit is going to help us understand how a function behaves as the values of x gets closer and closer to a specific value. Or another way to say it is the values of x get infinitely close to a particular point, and it helps us gain insight into the trends and the properties of a function. So for example, if we look at this in terms of business, it's going to help us assess risk and price trends and some other things. So what we're going to focus on is what are the properties of the function, what happens to the value of the function as your value of x gets closer and closer and closer to a specific value. This, let me put my pointer on. Whoops. Okay, so this is limit notation. So you'll see LIM that stands for limit, and then underneath here you'll see x approaches, and then the c represents some value. So as x approaches 5 or as x approaches -2. So, and then this is the function that we're evaluating, and then L represents the limit. So you would read this as the limit of f of x as x approaches, and then you name the number, and then you say that limit is L, and then whatever value that is. So to give an example, if you imagine, if you can see my pointer, if you imagine that the function is like a roller coaster track, and if you are watching how the roller coaster speeds up or slows down and the height as you are approaching a specific point on the track, you're paying close attention to what happens to the track as you get closer to a certain point on the track. And usually the most interesting points that we're going to be looking at is the weird ones, like what happens if you have something like this. So imagine that my pointer here is the roller coaster on the track. If I was following this and I want to look at this point right here at x equals 1. So as I come this way on the track, I would say as x approaches 1, the limit would be 4, because this is what I'm getting closer and closer and closer to. The value of the function is completely different concept than the limit, although sometimes or a lot of times they overlap, but they're different concepts. The value of a function is defined. So this would be the value of the function. If you see here, that's an open circle, so that indicates that there's no value there. So the limit is what we're getting closer to. We don't necessarily have to actually get to that point. It's just what we're getting closer to. So if I were to ask you, what is the limit of this function as x approaches 1, you would say 4, or it looks like a little over 4. And then if I ask you for the value of the function, you would say whatever that is, like 1.8 or whatever. And this note here, it's important, and we're going to go into this in more detail later. There's notation. If you notice here, it says the limit as x approaches c, and then it has a negative sign up where we would normally expect an exponent. That notation is called a one-sided limit because you're specifically looking at it coming in from one direction. If you see a negative, that means you're coming in from the left. If you see a positive, that means you're coming in from the right. So there are times where you're coming in from different directions, your limit might be different. And so coming in from the left, my limit would be 4.2 or whatever that is. And then coming in from the right, that would be as C approaches from the right, that would be the C with the plus. That means I'm coming in from this direction. And still, the limit in this case would be the same. And here's the note down here that I just discussed. The, the value of the function is different than the limit. There are three ways that we're going to talk about in this class on how to find the value of a limit. We're going to go through some examples of all three of these methods. There's numerically, which means using tables. There's graphically, which means you're literally just looking at a graph. And then there's algebraically, means you're using algebra manipulations, algebra properties to actually do direct substitution and solve it like you would solve anything else. So in this first example, we're going to look at the table method. So it says, find the limit as x approaches 2 of the function. When we use the table method, what we're doing is we're making a table of values from both sides of whatever it is that you're trying to approach, which in this case is 2. You're trying to approach 2. So we're going to create a table of values, and we're going to create values coming from the left and the right. If I look at the value of the function directly at 2, you can see we run into a problem because that would create a 0 in the denominator. So we can't use direct substitution here. So these are the values when we make the table. These are the values that are approaching from the left. So we're making the numbers closer and closer to 2. And you can see if we plug in 1, the value of the function is 7. And as we plug in 1.5, we get 8.5. And as we plug in numbers closer and closer to 2, so the closest value we have right here on the table is 1.99999. And that gives us 9.99997. So it's getting closer and closer to 10. Coming from the other side, we want to pick numbers that are bigger than 2, but getting closer to 2. So this table starts with 3, and it increasingly gets closer and closer to 2. And the closest value we have here is 2.00001. And so coming from the right, we are also approaching 10, but it's just going to be from a different side. So you can see that when we look at the table method, we can take a really good guess at what the limit is by noticing that both sides are getting closer and closer and closer to 10. So we could say, here's the notation, we could say the limit as x approaches 2 of this function is going to be 10. Now I want to show you how you can actually make these tables and see the graph on GeoGebra. To create a table of values on GeoGebra, you want to open the GeoGebra graphing calculator. You can either do this from within XYZ, or if you want to open it up and look at it on a bigger screen, you can just go to the actual online app by going to geogebra.org and then opening up the graphing calculator. So the first thing you want to do when you want to create a table of values for a specific function, you want to define the function. If you are looking at several functions at a time, you need to pay attention to how it's labeled because it's going to distinguish the difference between the functions with the name of the function in the table. So make sure you know how it's labeled. You can change your label by just clicking on it and then changing the letter that's in front. Once you have your function defined, and this is the example we were just working on, I'm going to click on the table. And then you can see that you have your X value list here. And then once you plug in your X's here, you'll see the value of the function automatically come up here. So since we are trying to see what happens as X approaches 2, I want to plug in values that are really close to 2 on either side. Coming from the left, we want to pick values that are smaller than 2, but we want it really close to 2. So I'll start with 1.9. I'll hit enter, and it tells me what the value of the function is here. And then I'll pick 1.999, and I'm just going to keep getting closer and closer. You can pick your own values. It doesn't matter as long as you keep getting closer and closer. Now you can see as I get closer to 2 from the left that I'm getting closer and closer to 10. If I plug in 2 directly, you'll see if I hit enter, it comes up blank because there's no value there. If I then go and put in values from the right, so that means I'm plugging in points that are greater than 2, but close to 2. So I'll pick 2.1, maybe 2.01, 2.00001, and I'm just going to get closer and closer. And you can see coming from the right, as I get closer to 2, my value of the function is getting closer to 10 as well. So this is how you can use your table. And then if you notice, you can check it on the graph. If I zoom in, it plots the points so you can see what happens as it gets closer and closer and closer. You just zoom in and you can see that it's getting closer and closer to 10, but it's not going to be actually, if you zoom in enough, you'll see that it's not actually on 10. It's just really, really close. So there's two more points here. These I think were the last two. Yep. If you click on the point, it will tell you what the point is. So that was the last point I tried. And then this one was the one coming from the left. That was the 1.9999. So that would be pretty helpful for you, I think, to visualize what's going on and to actually get the value of the function. Our next example involves that piecewise function from the previous section that we used to model the profit for that fundraising dance. And we had to create it as a piecewise function because there were different profit functions depending on the number of people that attended the dance. Now, if we look at the graph, the interesting point is x equals 150. When you zoom in really close to the graph near that point of x equals 50, you're going to see that we're going to be unable to find the limit of that function because if you're looking for the limit coming from the left as x approaches 150, it's going to be different than the limit coming from the right as x approaches 150. So let me get my pointer out. If I'm approaching 150 from the left, I'm getting closer and closer and closer to 2,900. If I approach 150 coming from the right, I'm going to get closer and closer and closer to whatever that value is here on the y-axis. So what we're going to do, we're going to look at 3 different limits. The first limit is as x approaches 145. If I'm coming in from this side or if I'm coming in from this side, the limit is going to be 2,800. For part C, we're trying to find the limit as x approaches 155. Because 155 lies on this piece of the graph, we're going to look here coming from both directions. So as we approach 155 coming from this direction or coming in from this direction, it's still going to be the same value. It's going to be 2,850. Now, some of these values might be hard to read off the graph because it lies in between 2 steps on the graph. So that's why it's handy to have that function as well. If the value that we're approaching lies on this piece here, this is the piece that represents the function that lies on the domain from 0 to 150. So that means I want to plug it into this right here. So I would plug in 145 here, take it times 20, and then subtract 100. As we approach 155, 155 lies on this piece of the graph, which lies between 150 and 350. So we want to use this piece of the graph. So I would plug in 155 in here. So I would take 20 times 155, subtract 250, and that's where I get the 2,850 from. Like we said before, the interesting part is when x is equal to 150. As I come and approach 150 from the left, I get a completely different answer as if I approach 150 from the right. If I wanted to know the value of the function at 150, that would be 2900. The value of the function lies here on this interval because it's a closed circle and we're including 150 in that domain for this piece. So this is a good graph to illustrate that idea that the limit can be different from the value of the function. Here's the table of values calculated from that function. And as you can see using the tables, as x approaches 150, then the value of the function approaches 2900 for that first piece, and that was coming from the left. If we're coming from the right, when the values of x are bigger than 150, but they're still getting closer and closer to 150, you can see that the value of the function is different. It's 2,750. It's different than this one here. So here's our theorem that talks about the difference between the one-sided limits and the two-sided limits. So this theorem tells us that the two-sided limit will equal some value if and only if the left-sided limit and the right-sided limit are the same limit. That's when, we'll call that limit L. If these two have the same limit, that's L, then the two-sided limit will also be equal to L. So this basically says that the right and the left limit has to exist and they both need to be equivalent in order for the two-sided limit to exist. So far, we covered examples where we can find limits by looking at the graph and by making tables. Now, limits of functions can also be determined algebraically, and we have properties to help us do that. If you look at other textbooks, it might be organized differently and it might have a different number of properties, but the meaning is the same. Now, this graph shows a constant function. So this is going to be the graph of f of x is equal to some value k, and k is where it crosses through on the y-axis. So no matter what value of x I'm looking at on the x-axis, I'm going to come up and my y value, no matter what, is always going to be k. So if we take the limit of a constant function, then no matter what, that limit is going to be the value of the function. So if I approach c from the left, the value of the function is k. And if I approach the function from the right, it's still the value of k. So the limit of a constant function is just going to be that constant itself. So this is an example of the constant function. If we have a constant function f of 4, and we're trying to find the limit as x approaches 7 of that constant function, the limit is going to be 4 because no matter what x value you're sitting at on the x-axis, your value of y is always going to be 4. So when you're approaching 7 on that function, all the values will be 4, and therefore the limit has to be 4. Now for a polynomial function, we can use direct substitution. And this works if you can easily plug that value of x that you're approaching into the function without breaking any math rules. Like we don't want to have division by 0 or negative under a square root or anything like that. Because polynomial functions don't have any weird points like that and have a domain over all real numbers, we're not going to run into any issues like that. So with polynomial functions, we can just use direct substitution. For this example 4, you can see that f of x is defined as a polynomial function. And I want to find the limit as x approaches 2. Because I know that this is a polynomial function, I can literally just plug 2 into x and it will give me the value of the limit. So I'm going to plug in 2 here and I'm just going to evaluate the function and I'm going to get the limit is 3. You can verify it by looking at the table. You can see coming from the left as we get closer and closer to 2, we're getting closer and closer to 3. Coming from the right, getting closer and closer to 2, you can see again that we're approaching 3 for the value of the function. And you can look at it graphically as well. The next property is what happens when you're taking the limit of a rational function. So the limit property of a rational function, this basically says that the limit of a rational function can be determined by direct substitution only if that substitution does not produce 0 in the denominator. So if I am finding the limit as, say, x approaches 3, I can plug in 3 into the numerator polynomial, and then I can plug in 3 into the denominator polynomial. And as long as that doesn't produce a 0 in the denominator, I can use direct substitution. If that does create a 0 in the denominator, then we have some other tricks that we can use that we're going to look at in a little bit. So here's an example using the property for the rational function. So this is my top polynomial, and this is the bottom polynomial. And I recognize that they're both polynomials. And I want to find the limit as x approaches -2. Because if I plug in -2 in for this x and it doesn't create a 0 in the denominator, I can just use direct substitution. So I'm going to plug in 2, or -2 actually, everywhere, and just simplify it. And I'm going to get that the limit is 1/3. The next property is talking about sums and differences of functions. So we're talking about when we have two functions that we're combining. That property basically states that if you have the sum or the difference of two functions, the limit can be calculated using direct substitution, provided that the limits of the individual functions exist. So again, we're looking at, when we use direct substitution, is there anything funky going on? Is it going to create any weird results like 0 in the denominator or negative under a square root? Those kinds of things. If not, we can use direct substitution. So here we have, so they're looking at this as a separate polynomial. It's just a monomial, one term. This as a separate polynomial, and this as a separate function. This is not a polynomial, but we have 3 different functions. And so this is saying that as long as I don't have an issue getting 0 in the denominator or anything funky like that, I can use direct substitution. So all I would do is plug in -1, and I can find the limit for each of those separately and then add or subtract them together. This property says that if I have a function that's being multiplied by some constant, and I try to take the limit, this is basically saying as long as the limit exists for the function f of x, I can take that constant out and I can just find the limit of f of x and then multiply by k. For product of functions, same idea. As long as the individual functions have limits at the point that we're approaching for x, then we can find the limit of each separately and multiply them together. So looking at example 7, we're going to do 2 things. We are going to use part A, which is f times x squared, to show the constant times a function. And then in part B, we're going to use the product rule. So in part A, I have 5 times x squared. I can pull that 5 out and find the limit of x squared and then multiply by 5, because I know when I plug 1 into x squared, I'm not going to run into any issues. So I can again use direct substitution here. The limit of the product is the product of the limits. That's what that product rule says. As long as each individual function has a limit that exists at the point that we're approaching, in this case x is equal to 1, we can use direct substitution. We can just find the limit of each individual function and then multiply them together. The limit of a quotient is the same idea as the property for rational functions. We just want to make sure if we're using direct substitution so that the limit in the denominator does not equal 0. So using 3x minus 2 over x plus 1, so we have a top function and a bottom function. I'm only concerned really about the denominator. If I plug in -2 here, I'm not going to run into a problem with having 0 in the denominator. So I can just use direct substitution, where I plug it into the top and the bottom separately and I just divide. The limit of a power of a function, same idea. It's consistent throughout all of these properties. I can use direct substitution only if this function doesn't create any issues when I plug in c. In this case, I'm plugging in 1/5, and I have 5x minus 3 raised to the power of 5. Because when I plug in 1/5, I don't get anything weird or funky, I can just use direct substitution. So I can plug in the 1/5, figure out what's inside the parentheses, and then raise it to the 5th power, and that will give me my limit. So this property is stating that if you have a radical and you want to find the limit of the nth root, whatever that root is, it can be determined by direct substitution as long as the limit of the function that's under the root exists. So far in the lesson up till now, the limits that we looked at have been determined by using tables or looking at the graph or using the limit laws in direct substitution. But sometimes we cannot use direct substitution, and now we're going to walk through a group of examples that show us what to do when that happens. For these examples, you really need to have a good foundation in algebra. So if you forget how to do something from algebra, please let me know and I'll provide some resources to help you review. Another thing that I want to mention while we're talking about this, we're going to start involving infinity into these examples. And when we say that a limit is infinity, it doesn't mean that the value is infinity, because that would imply that infinity is some number. And infinity is not a number, it's a concept that the function grows without bound, and it can go in either direction. It can go in the positive or negative direction. So I just want to make sure we're clear that infinity is not a value. Looking at part A, it says the limit as x approaches 2 of the function f of x. When we look at f of x, we can plug 2 in without running into any issues. So in this case, I can use direct substitution. So I would plug 2 in here, use order of operations to evaluate it, and we would get that the limit is 1. And we can verify that by looking at the graph. If I'm coming towards 2 this way, I'm approaching 1. And if I come from the right, I'm still approaching the function value of 1. So we have that the limit as x goes to 2 is 1. When we look at part B, as I approach 3 from the left, here's 3 right here, we can see that there's a vertical asymptote there. And as I approach 3 from the left, the value of the function is increasing without bound. It's not going to approach a specific value. It just keeps growing and growing. When I approach 3 from the right, I get the same thing. Coming from the right, the value of the function keeps increasing and increasing without bound. So in this case, because both one-sided limits approach infinity, then I would say that the limit as x approaches 3 is positive infinity. Now keep that in mind, because when we switch to the next slide, we're going to look at an example where there's an asymptote, but there is no limit. The author of the book chose to use the wording does not exist for the limit as x approach 3 because we're not approaching a specific value. But for me, if both one-sided limits are approaching the same thing, in this case, they're both approaching positive infinity, I would just say that the limit as x approaches 3 does exist because both of those one-sided limits are approaching infinity, positive infinity specifically. So for me, I would say that the limit is positive infinity, but you have to remember that it's not a value. In the last part, we need to find the limit as x approaches 5. If I try to use direct substitution, I can in this case because I don't run into getting 0 in the denominator. So I can use direct substitution here. And when we calculate that, we're going to get 1/4. If we look at the limit as x approaches 5 from the left or from the right, we can see that they both approach the same value. Now, it's hard to read what that is on the graph. And when that happens, instead of looking at the graph, it's better to just plug in the value into the function. When we look at example 12, we need to find the limit as x approaches -1. And we have a rational function here where we have a polynomial on the top and on the bottom. When we try to use direct substitution, that's when we run into a problem. So if you look and we plug in -1, we're going to get -1/0. That's undefined. Now, when we get something like that, we really want to try to make an effort to do some kind of trick to make it so that we can use direct substitution. In this case, there isn't a way to do that. And you can verify it with the graph. When we look at the graph, there is no limit here at x equals -1. There's a vertical asymptote there. But this example here, this graph is different than the previous graph. Let's look at that again. Let me go back up real quick. Remember we said that the limit as x approaches 3 from either side, they're both one-sided limit is approaching infinity. So we would say the two-sided limit is positive infinity. For this example here, the one-sided limits don't agree. If I approach -1 from the left, I'm growing without bound in the positive direction. If I approach -1 from the left, I'm going down without bound. So that's going to be negative infinity. Because the one-sided limits aren't the same, we would say the limit does not exist. Now, when we run into cases where we have weird situations like 0/0, we need to try to use some algebra tricks to manipulate the function in a way that we can use direct substitution. And that's what I mean by being creative. Before I go through some of the common methods, I want to go over what this means. When you encounter 0 divided by 0, this is what's known as an indeterminate form because we don't know what this means. It could mean many different things. There are other kinds of indeterminate forms, but this is just one. And the reason why I say this could mean many different things, and I know that sounds weird, is because it literally can. If I take 8 divided by 4, I know that's 2. Intuitively, I know that that's 2. And then if we want to prove that it is, or check, we would work backwards and take this number times the divisor and check to see if that's equal to 8. And it does. This example is well defined. We don't have any confusion on what equals what. I know it sounds weird, but 0/0 has many possible answers. If we use the same idea as up here, when we work backwards to check, if I take 0 divided by 0 and I set that equal to 5, and I want to work backwards to check to see if it works, I have 5 times 0 is equal to 0. It works. Now, if I set it equal to something else like -0.01, if I take -0.01 and work backwards and take that times 0, I'm going to get 0. That's another true statement. No matter what real number I put in here, it's going to work. Because whatever real number is here, when I multiply it by 0, I'm going to get 0. So that's why this is a little confusing. It's not well defined. So in these weird cases, here are some algebra tricks that you can use. Now, this isn't all of them, but these are the most common that we're going to use repeatedly. The first one is you could try to rearrange the function by combining fractions or splitting up fractions. Another one is you could rationalize the denominator. And actually, I should have put in there, you can rationalize the denominator or the numerator, because that can work both ways. So make sure you add that to your notes, put that addition in there. You could factor and simplify, and usually you want to use that when you have a rational function where you can factor a polynomial on the top or on the bottom and then cancel some factor and then simplify. And another one is, and this might be confusing at first, but when we walk through an example, it will make more sense. You can find the highest exponent of all the terms in the function, whatever the highest exponent is, and then divide all the terms in that function by x raised to the power of whatever that highest exponent is. So looking at example 13, we have the situation of a rational function. We have a polynomial divided by a polynomial, and we're trying to find the limit as x approaches 2. Here's where we run into a problem. If I plug in 2, I get 0 over 0. It's one of those indeterminate forms. So this is where I have to be creative and figure out a way around this. Normally, when we have a rational function like this, you should try the trick of factoring. Most of the time it works. So if you look down here, if I factor the numerator, it factors to x minus 2 and x plus 1. So I can cross off and get rid of the x minus 2's. That leaves me with x plus 1. So if I find the limit as x approaches 2, now I can use direct substitution and I get 3. One thing that I really want to stress here, this equality right here, that's saying that the limits are equal. We're literally writing that down. The limit as x approaches 2 of this function is equal to the limit of this function. That doesn't mean the functions are equivalent. If I graph the first function and then I graph the function after I simplify it, these are not the same function. These two will look exactly the same, except there won't be a value at x equals 2 for this function. We will have what's called a removable discontinuity. So be very careful and don't misunderstand this equality sign. It doesn't mean the functions are equivalent, it means the limits are equivalent. When we look at it graphically, this is our rational function. When we simplified it above, we got the line x plus 1, but the line x plus 1 is not the same as that rational function. The limits are the same. Those two functions are the same except at the point x equals 2. The line x plus 1 has a value at x equals 2, but the rational function does not have a value at x equals 2. And then you can also verify the limit by looking at the tables. Example 14 is another case of a removable discontinuity, but this is an example that involves radicals. For this example, we want to find the limit as x approaches 4 of the function square root of x minus 2 divided by x minus 4. If I use direct substitution, I'm going to run into this problem of 0 over 0 again, so I need to be creative and use some algebra tricks. When you're dealing with radicals, most of the time, but not all the time, using the conjugate to rationalize either the numerator or the denominator might help clear up this problem. Now, to rationalize either the numerator or the denominator, you need to use what's called the conjugate. This should be a review, but just in case, the conjugate, this expression here on the top, and you literally just switch the sign in the middle. That's the conjugate. And what's going to happen is that when you multiply it out and simplify, it works like the difference of squares, where the middle term is going to cancel because you're going to have the same exact thing when you multiply it out, but one's going to be plus and one's going to be minus. So all that you're left with is the first term squared and the last term squared. We're going to rationalize the numerator because that's where the radical is. We're going to multiply the top and the bottom. You have to remember whatever you do to the top, you have to do it to the bottom as well. That way we're multiplying by 1. So when we multiply this out, we're going to get the square root of x times the square root of x is x. And then we're going to get -2 times +2 is a -4. And then the middle term is going to cancel because we're going to have plus or minus the same thing. Down the bottom, we just take x minus 4 times square root of x plus 2. As you can see, the x minus 4 in the numerator will divide out with the x minus 4 in the denominator. These two, x minus 4 over x minus 4, becomes 1. So then we're left with 1 over the square root of x plus 2. So now we have rearranged it so the limit of the original function is equal to this limit here. And now because I rationalized it, it's set up differently, where I can plug in x is equal to 4 and use direct substitution. And when I do that, I get 1/4. Now this is another case where the limit is the same, but the two functions are not the same. So the original function given is not the same as this simplified function. And we said that we had a removable discontinuity at x equals 4. That's right here. That means there's a hole in the graph because that value doesn't exist. Now we're going to talk about finding limits as x approaches positive or negative infinity. And when we're looking at what happens to the function as x gets really, really big or as x gets really, really small, we're thinking about where the function levels off, if it levels off. Because when we find the limit as x approaches positive or negative infinity, we're looking what happens long term, like way far out to the right and way far out to the left. So we have this property here. It says the dominant term property. And if we have a rational function where we have a polynomial on the top and the bottom, we want to use this property to help us figure out what happens as x approaches infinity. It means when we're finding limits, the dominant term is the part of the function that grows the fastest. As the variable gets really big or really small, it's like looking at which part of the equation has the most significant impact on the overall behavior of the function as you approach a specific value. So the dominant term is going to help us understand where the function is headed when you look long term to the right or to the left. So when we're dealing with limits as x approaches infinity, we have some properties that we're going to use, including this one that we just discussed. The first property is if you have x raised to some power and n is greater than 0, this is really important because this property won't work if n is less than 0. So if we have the limit as x approaches infinity of x to some power of n that's positive, we're going to get infinity. So now we're looking at x to the n in the denominator. And if I find the limit as x approaches infinity, in this case, that's going to be 0. As this number in the denominator gets bigger and bigger and bigger, the entire fraction is going to get smaller and smaller. So example 15, we're going to divide the numerator and denominator of the rational expression by x squared to help evaluate this limit. So that was the trick that I talked about. We're going to find the largest exponent of all the terms in the function, and we're going to divide all the terms in the function by x raised to that power that is the largest. So when we look at this, if I consider what happens as x approaches infinity for this function in the numerator, that's going to approach infinity. And the limit of the bottom as x approaches infinity is going to do the same thing. It's going to approach infinity. So we'll have infinity over infinity. So we're going to divide all the terms by x squared. I'm going to take 5x squared divided by x squared. That's going to leave me with the 5 right here. I'm going to take 7x, divide it by x squared, and that's going to leave me with 7 over x. Then I'm going to take negative 2 over x squared, and that's going to leave me with minus 2 over x squared. Then I do the same thing in the bottom. I just divide all of these terms by x squared, and this is what we're going to get. Now we can see what's going on because by using that trick, it helps us determine what the limit is. Because if I start thinking about this term and this term as x approaches infinity, that means the bottom here and here is going to get super big really fast. So both of these fractions, 7 over x and 2 over x squared, are both going to get closer and closer to 0. And it's going to get so small that we can just call it 0. So I'm left with 5 on the top. Then the same thing on the bottom. If I think about these two terms here as the value of x gets bigger and bigger and bigger, that means the whole fraction is going to get smaller and smaller and smaller. Where it's so small, we can just call it 0. So we're left with just 8, which tells me that the limit is going to be 5 over 8. When you think back to algebra class and you think about horizontal asymptotes, this is exactly what we're doing. Instead of looking at those 3 rules about what to expect for the horizontal asymptote, we're figuring out what the asymptote is by using limits. If you remember the rule, if the degree on the top, x squared, is equal to the degree on the bottom, same thing here, x squared, if these degrees are the same, you look at the leading coefficients to determine your horizontal asymptote, which is 5/8, and that's exactly what we did right here. Now we're going to do example 16 using the same idea. The bottom and the top would both approach infinity. So I would get the indeterminate form infinity over infinity. So I would use the trick where I would take all the terms in this function and divide it by x to the third because 3 is the largest exponent. When I do that, I'm going to end up being left with 8x over 5. And as x gets larger and larger and larger, that makes the numerator grow really fast, which means the overall function is getting really big really fast. So it's going to increase without bound. Now, if you look at this, notice the degree on the top is larger than the degree on the bottom. That means this is going to grow way faster than this term down here in the denominator of 5x squared. So 8x to the third is going to be the dominant term. This is what's going to cause the function to have a limit as x goes to infinity because this term is going to grow way faster than the 5x squared in the denominator. Looking at this function here, we have where x squared is in the denominator and we have x in the numerator. This grows way bigger, the 2x squared grows way bigger than the x in the numerator as we plug in values that are bigger and bigger and bigger. If 2x squared is the dominant term, because it's going to grow faster, that means the numbers in the bottom are going to grow way faster than the numbers in the top, which means the fraction is going to get smaller and smaller and smaller. So our horizontal asymptote is going to be 0. So this, if you think back to your algebra horizontal rules, this is the rule where we say if the degree in the denominator is bigger than the degree in the numerator, the horizontal asymptote is going to be 0. This is exactly why that happens. So here are the overall rules for finding horizontal asymptotes using the concept of taking the limit as x approaches infinity, and it can go to negative infinity as well. These are the rules that we just discussed. So now we're going to do some more examples. We have each of the following limits results in the indeterminate form infinity over infinity when we do direct substitution. We're going to use the dominant term property to evaluate each of these limits. This limit here as the value of x approaches infinity, meaning we're plugging in values that are getting bigger and bigger and bigger. The dominant term is going to be in the denominator because this is x squared and this is x. So the bottom is going to grow way faster than the top, which means this is going to approach 0. Now here is the graph of example A. So the graph is going to approach 0 long term in either direction. So it's going to flatten out. As x approaches positive infinity, it's going to flatten out at 0. And the same thing here. It's going to just flatten out here at 0 too long term. For part B, we're looking at 2x plus 1 over x minus 3. The degrees on the top and the bottom are the same, which means there really isn't a dominant term. So this is the case where we want to take the leading coefficients. So I would take 2 over 1 and get 2. So the limit as x approaches infinity is 2. Now this graph was on the previous slide, so let me back up. That was this right here. So if I follow the graph as x goes to positive infinity, it's going to level out at 2. And same thing this way. And if I go to negative infinity, it's going to level out at 2. For part C, this is the example where the degree on the top is bigger than the degree on the bottom. So the dominant term is going to be in the numerator. So the numerator is going to grow way faster than the denominator, which means we're going to have a limit of infinity. In this case, we don't have a horizontal asymptote. We have what's called a slant asymptote. So the asymptote is like a slant line. So that is how limits are related to asymptotes. When we're looking at horizontal asymptotes, we're looking at what happens long term to the left and to the right, or how does the function behave as x goes way out to the right or way out to the left. Now, vertical asymptotes involve limits as well, but we're just looking at the vertical asymptote as it approaches a specific value, and then the value of the function would grow without bound in either direction, positive or negative infinity. So let's look at example 19. We have the function below was used to previously model the progress of a person on a diet with a starting weight of 200 pounds. The function w of x is the weight of the person after x weeks of dieting. So here's our function, and x has to be positive because if x represents the weeks, we don't want to have negative weeks. That doesn't make sense in the context of what we're talking about. When we're looking at this function, if I look at the top, the degree of the top is 1, the degree of the bottom is 1. So this function doesn't have a dominant term. When the degree on the top is equal to the degree on the bottom, we look at the leading coefficients. The leading coefficient for the top is going to be 160, not 80 because we have to distribute that 80. So the leading coefficient will be 160. On the bottom, the leading coefficient is 1, and then when we divide, we're going to get that our horizontal asymptote is at 160. So if I go in either direction, to the right or to the left, it's going to flatten out at 160. Our vertical asymptote is going to occur right here, and that's when the value of the function increases without bound in either direction. So this would be at the value of -6. So here is our vertical asymptote at x equals -6. And then this is how we decided on the horizontal asymptote. We looked at the leading coefficients because the degree on the top and the bottom were the same. If we interpret this, it means that a person with a starting weight of 200 pounds will lose weight quickly at first and then gradually reach a lower limit of 160 pounds. So here's our self-check. After you practice your homework, you want to try to answer these questions. These are conceptual questions that you have to explain. And if you feel comfortable and confident with your answers for these, then you probably mastered the topics that are in this lesson. If you don't understand these questions and you need help, just let me know.